Hi everyone, the previous video ended with the unsuccessful repair. All the measurements looked normal, but the board still did not post. After publishing that video, I received a lot of ideas and suggestions from you, so I'd like to take a couple of minutes at the beginning of this one to go through your questions and test some of your proposal. That way you can actively participate in the repair process by sharing your ideas in the comments. It could be something with VRM. So all phases provide stable pulse modulation, so the VRM is working. There still could be internal damage to the VRM controller, but the only way to confirm that is to replace the controller, and I would like to leave that as a last resort. Q-Flash IC issue. So we have a Q-Flash button here, and the only issue I can imagine is that it is shorted because the button itself is damaged. So I guess we can check it and measure the resistance. Do we have any short here? There's 3 pins, 3 grounds, and 1 is the signal. I guess the signal is that one. Let's check another one. Those grounds, right? Yeah. So what about this pin? This pin is not shorted. So when we press the button, it should be shorted. So the button is working and there's no short. Q-Flash consists of a button and the BIOS controller, usually the chip labeled BIOS with large capital letters. If the Q-Flash button is internally shorted, the board disables the BIOS chip for reading by deasserting the chip select signal, effectively taking exclusive control over the BIOS chip. So what can we do? We can measure the resistance of the Q-Flash button first and make sure it's not shorted. If it were shorted, we would not see any packet transmissions between the BIOS and the CPU, but in our case, we do have communication. Another idea is to connect a speaker, buzzer, or debug card. I have a debug card, TL611 Pro. This debug card doesn't show anything when I plug in to the any of the PCI Express. It's useless. However, we can check and power on with the buzzer and see if we have any sounds or beeps during the power on. So let's do it. And the current consumption goes here. We have 115 milliamps. So pressing the power button switch. So as you can see, there's no any beeps. Something else gave up before the CPU could sustain damage. If that could still damage a CPU? That's the question. Yes, it can, and I believe it did. So I tested this CPU on another motherboard. It boots into Windows, but it is drastically lagging. I do not see this behavior with my other AM4 test CPU, so I assume some internal logic inside the CPU was damaged, and it likely needs replacement. However, my other known good CPU does not power on this board, which brings us back to the motherboard. It could be something with the chipset. Yes, it is possible that the chipset is internally damaged. The motherboard components communicate over digital protocol like VID. This is not just an analog signal we can measure with a multimeter. It is byte-level digital communication, which realistically can only be deeply debugged by the manufacturer. And today, the industry rule is usually simple. Working, use it. Broken, replace it. Flash different BIOS. So I tried 3 different BIOS versions, no changes. Everything looks like it's working, except one tiny thing that ruins everything. So that's it for the questions and answer part. Thank you for all your ideas and suggestions. I really appreciate your involvement in the diagnostic process. It makes this repair much more interesting because we're not just fixing a board, we're analyzing it together. If you have more thoughts about watching this video, leave them in the comments. I read everything, and sometimes your idea becomes the key to the next step. Now let's go to the repair of a new motherboard. Everyone, all right, today on the bench we have an ASUS TUF Gaming X570-PLUS Wi-Fi. Customer states the board power zone, but there's no post. So first, we're not assuming anything. We're going to verify everything from the ground up. Let's start with the visual inspection and then follow to the resistance measurements. Okay, let's measure resistances on main power rails. Okay, 2.3 volts, we have kilo ohms. 5 volts, we have 1.3 kilo ohms as well. 12 volts, so there's a kilo ohms as well, so no short. 5 VSB, 5 volt standby rail, it's 9 kilo ohms, which is perfect. So the minus 12 volts, there is no resistance measure. And about the coils, so I guess this coil is the resistance for the power line for the PCH, for the south bridge. And it's just 120 ohms, 117 ohms. Looks normal. It's probably here the 2.5 volts. Memory power rail, it's 21 kilo ohms, which is nice. Somewhere here it should be a 5 volts. Yes, it's here. And this is kilo ohms as well. What else? Okay, so let's measure the 12 volt CPU. And 12 volt CPU is kilo ohms. Then 12 volts to V core. We have mega ohms, and the V core itself 60 ohms. Okay, and the SOC 59, okay, 60 ohms as well, and SOC to 12 volts, kilo ohms as well. Okay, looks normal. Let's make a visual inspection under the microscope before powering on. Just a quick look at what is not covered by heatsinks and PCH fans. Okay, we will start from the SIO area. SIO itself, the chip looks good, and the circuitry is, here I found a problem, and this is a resistor. There is a scratch, you see it as well. I guess this is the culprit because without this resistor, the board could not start. I'm not sure. Let me check real quick. What is this resistor for? Okay, so this resistor is basically the pull-up resistor for deep sleep S5 state. Before we continue with the diagnostics, I want to explain something important, the power states of the motherboard. So you'll often hear references to S0 through S5 states. Those are ACPI system power states, and understanding them is critical when diagnosing no power or no post issues. So let's break them down. S5, that's a soft off state. Well, the system appears completely off to the user, but it's not truly dead. The power supply is still providing 5 volt standby power. The standby voltage powers the SIO chip, the power button circuitry, and sometimes network wake-up logic. If 5 VSB is missing, the board cannot leave S5, so pressing the power button will do nothing. When you press the power button, the SIO detects it and sends a signal to transition the board from S5 to the next state. State S4 is a hibernation, so the system state is safe to disk and almost everything is powered down. So we will not use it in repair, so I just omit it. This sleep S3 state. The S3 is the traditional sleep state. In this state, CPU is off, most power rails are off, but RAM remains powered. Memory must stay powered because it holds the system state. If the RAM rail is unstable, system may fail to resume from sleep. This often happens when there is no stable power and there is a degraded caps in the RAM power lines, 2.5 volts, 1.2 volts, or 0.6 volts. And the state S0, there is no state S2 or S1. S0, it's fully on, so it's a working state. All main rails are active. 12 volt CPU, V core, 3.3 volts, 5 volts, RAM voltage, chipset voltage, the CPU is executing code, BIOS is running, post happens in S0 only. So when we say board doesn't reach S0, it means it never completed the power sequence. So what happens between S5 and S0? So this transition is where most motherboard failures occur. Well, the sequence roughly goes like this, like 5 USB present, power button pressed, SIO asserts power button signal, PSU enables main 12 volts, 5 volts, 3.3 volts, PCA releases sleep signals, or in case of the AM4, usually the CPU releases sleep signals. It's sleep S5, sleep S3. VRAM enables, CPU vCore appears, BIOS execution begins. So if any signal in this chain is missing, the board gets stuck between states. For example, there's no 5 VSB stuck in mechanical op. No sleep S5 release. Board never leaves S5. That's what we have here. So the resistor prevented the releasing the sleep signal. And so there is no reaction to the power button. The board thinks it's in S5. Like no vCore, CPU never enters S0. Like no BIOS activity, system powers but no post. When we're troubleshooting, I'm always asking like which state is the board stuck in. So it's not leaving S5. It is attempting S0 but crashing. It is looping between states. Once you understand S states, motherboard diagnostics becomes much more logical instead of random probing. Let's go back to the repair. Okay, so this resistor is basically the pull-up resistor for deep sleep S5 state. And I guess that without that resistor, we don't have a 3 volts in this control power rail. And so that means that the SIO will not power it on. I'm not sure, but we can test and try to power it on. Let me remove this resistor. I don't know what is the value of this. And I guess we better measure it. Okay, so in order to measure this resistor, we're going to use this kind of probes with our multimeter. It's more handy when you need to measure such a small resistor. Yeah, it's 55.8 kilo ohms. Okay. Now we know that even if we lose it, we can use a new one. Let's go back to the inspection of the board. We need to check other areas. Maybe there is something knocked off as well. I don't think that this scratch actually broke any traces. Let's go to our BIOS. It doesn't look like BIOS has been desoldered. There's no heat damage as well. Let's go to the CPU circuitry. Any scratches here? There's a scratch, but it's just the surface one. So here we usually have fans and RGB. Okay. So what I can assume, like this is for, according to the schematic, this MOSFET is for the green light. So this is a red, green, and blue. So this is the green one. And so I guess maybe somehow the green light was short at 12 volts in past. But who knows? Okay, let's go the 2.5 volts MOSFETs in the area. And so, okay. Everything other is covered by the heatsinks. And so what we would need to do is to flip the board upside down and inspect the back of the board. So we'll start from the CPU area. And I see that the CPU area looks good. There's no damage. Okay, let's see the vCore and SoC. So VRAM caps. all are in their place here. Let's look at the under the PCH. And let's remove the glare a bit. So here it looks fine. So that's it. Let's try to power it on and to see if there will be a power button reaction without this resistor over here. Okay. Pressing the power button, should not be any reaction without the AM4. Let's look. Yeah, there's no reaction without the AM4 CPU. Let's put the CPU in. Let's use 3200G as usual, the cheapest one. Power it on. And that is almost 90 milliamps, 87. So pressing the power button, and we have no reaction because the board is in constant sleep S5 state. Let's solder this resistor and check if it helps. Okay, so let's check if it helped. So resistor is in place. Now we will power on. Put our power button. Now we have 150 milliamps. So pressing the power button, and of course we have a DRAM LED eliminated because there's no DRAM here. Turn it off. Let's put DRAM and check if we have picture. We're going to use the A2. The A2 is the slot number 4. Here. Then we need a capture screen. Capture screen. And need a post screen here. So right now, power on. And I guess a small heatsink for the CPU. Pressing the power button. 40 watts. Okay. VGA boot. Do we have a picture? Let's see if we have a picture. Do we have the post screen here? Come on. Yes, we do. Okay. So let's see what we have here. And here we go. That's the picture. Okay, so let me see what BIOS we have. So we need an advanced mode F7, go to F7. And we have a BIOS of 2022, so it is basically 4 years outdated. Okay, let's turn it off. This turned out to be one of the easiest repairs, but it's a good reminder that motherboard inspection requires real attention to details. Finding a tiny knocked off component like that isn't always obvious, and it's easy to miss if you're not looking carefully. It's always satisfying to bring a board back to life when it could have been thrown away over a single small resistor. If you have any questions, leave them in the comments. I read them all, I answer them, and I really appreciate the interaction. It makes the repair process even more interesting. I've already received some new AM5 boards for repair, and if those turn out to be interesting cases, the next video should be a good one as well. See you in the next repair!